Today we're starting on our final week of new lessons, and today is the graphing part, which is going to be also the part next time. Today we're going to look at the graphs of sine and cosine. So you should have a chapter 4 handout available to you, and first part of it says for every real number, x is the domain of the f. Every integer n is some positive number p. The least possible positive value of p is the period of the function. The circumference of the unit circle is 2 pi, and that was the famous wrapper. So the least value of p for which the sine and cosine functions repeat is 2 pi. Therefore, the sine and the cosine functions are periodic functions with period of 2 pi for every positive integer n. So, sine of x is equal to the sine of x plus n times 2 pi. That is the periodic tendency of pi, and the same thing with cosine. Cosine of x is equal to the cosine of x plus n times 2 pi. So, however many times it repeats is showing where you are along the graph. Again, the graph being periodic. Now, from 0 to pi over 2, sine graph does this. Think about what sine is in the first quadrant, and I'm going to mark the graph off like this. It's different from what you probably have. We're going to have Q1, Q2, Q3, and finally Q4. Now, in those times, if you think about what sine is positive in the first quadrant. Sine starts off at 0, and the first quadrant ends at pi over 2. So it starts off at 0, and it grows in a concave downward motion to the point that is pi over 2, 1. Now, the next portion represents the second quadrant, and the second quadrant goes from pi over 2 to pi. And it remains positive, but at pi we end up back at the sine being equal to 0. So, we have positive values in the first and second quadrant. Now, third quadrant, we run into the situation where pi is negative again. I'm sorry, not pi, sine is negative again. And we go from here to 3 pi over 2. And this time we drop down to negative 1. And then finally the fourth quadrant stretches out to pi. And we're here. Now, if you think about the nature of the unit circle goes around for a measure of 2 pi radians. After it hits 2 pi radians, the values keep repeating. That's built into this concept right here. So, from this, we end up repeating the pattern in this direction. And likewise, we can do negative angles. If we go clockwise, we go negative. Well, we're clockwise, we're in the fourth quadrant, so it goes back down to here, up, and back down, and it goes, like we said, forever and ever and ever and ever and ever. So that is a cyclical pattern of it. So here we have sine increases from 0 to 1 between 0 and pi over 2. From pi over 2 to pi, we decrease from 1 to 0. From pi to 3 pi over 2, we decrease from 0 to negative 1. And then from 3 pi over 2 to, I should say 2 pi, we increase back from negative 1 to 0. Now let's look at the graph of cosine, and we're going to look at it with a little bit of the same pattern. I'm going to drop my quadrants down. Now, if you remember from this, cosine's graph starts at positive 1, and from positive 1, it goes down to 0 at pi over 2. And it needs to, because by the time it reaches the second quadrant, cosine has to be negative again. So we're negative down to negative 1. And then we hit pi. Well, now we're in the third quadrant. Cosine is still negative, but it gets back towards 0, where it's at 0 at 3 pi over 2. And then finally, going back, we hit the fourth quadrant again, where cosine is positive. So we go back to positive 1, and again, we repeat that cycle again. It goes into the x plus n times 2 pi. So we have cosine decreasing from 1 to 0, from 0 to pi over 2, decreases from 0 to negative 1 between pi over 2 and pi. It increases from negative 1 to 0 between between pi and 3 pi over 2. And then finally from 3 pi over 2 to 2 pi, we increase and we are back to being positive. So we increase from 0 to 1. Now, the domain values for sine and cosine, and we're looking at both pages 2 and pages 3 right now. We're going to go a little bit back and forth. Theta, sine theta, cosine theta. And we're going to start here at 0. And then from 0, we're going to go to pi over 6, pi over 4, pi over 3. Until we get to pi over 2. Now, the values end up being very similar, exactly the same for sine in the second quadrant, but in cosine, we're just looking at the negative values instead of the positive values. So I'm just going to skip down to pi, and again, that's what your chart does. Then we're going to skip to 3 pi over 2, because again, the patterns repeat within the quadrants. And then finally, we get back to 2 pi. So we're looking here, and in this, the sine of 0 is 0, related to that graph point. Cosine of 0 is 1. Now pi over 6 is a 30-degree angle, and we can go back to the 30, 60, 90 triangle. So for 30 degrees, which is pi over 6, we've got a sine of 1/2. And our cosine is the square root of 3 over 2. Pi over 4, again, that's a 45-degree angle, so we can look at the isosceles right triangle. And we label it 1/1 square root of 2. So for pi over 4, we get this 1 over the square root of 2, which rationalizes to be the square root of 2 over 2. And again, opposite and adjacent are the same, so we stick with square root of 2 over 2. We get to pi over 3. Now we're back to the 60-degree angle. Sine is the square root of 3 over 2, where the cosine is 1 over 2, or 1/2. And now we're back to pi over 2. Well, what happens at pi over 2? Now our sine becomes 1 and our cosine becomes 0. Now looking back at the graphs, here our sine is 0, our cosine is -1. Here at 3 pi over 2, we've got a sine of -1 and a cosine of 0. And then back to 2 pi, which is a coterminal angle with 0. We get 0 and 1 again. So that fills out that chart. The range, again, for both of them is -1 to 1. -1 and 1 both being included. So if you wrote that in interval notations, you would have the brackets there. The graph is continuous over the entire domain of -infinity to infinity. Why is that? There is not an angle that we cannot take the sine of. Now, we don't get sine values greater than 1 or less than -1, but there is not an angle that we can't take the sine of. The x-intercepts have x values in the form of n pi, and where n is an integer and it has a period of 2 pi. The graph is symmetric with respect to the origin. Again, if you remember, we called that an odd function when we had symmetry about the origin. And that meant that the sine of -x was equal to the negative of the sine of x. All right, now its domain consists of real numbers corresponding with angle measures, and its range corresponds with the y values. Likewise, we've started the chart for the cosine values, which is on the next page. Again, just like sine, it is continuous over the domain, and the domain is -infinity to infinity. The range is still -1 to 1. It's in the form of 2 pi plus 1 times pi over 2. For the x-intercepts, period is 2 pi. The graph is symmetric with respect to the y-axis, so its function is an even function, which means that the cosine of -x is equal to the cosine of x. Even functions, again, reflect about the y-axis. So if you put a mirror here at your y-axis, it would come back and do just exactly what it's doing, going off in that direction. Now, the next part says that we're going to look at the graph of y equals a sine x. And a sine x is just the a represents your amplitude. And as long as there's not something being added or subtracted from it, the range of this would consist of going from -a to +a, unless a is negative, and then if a was negative, it would be from a to -a. Now, looking at the graph of y equals 1/2 of the sine of x, its range would be -1/2 to 1/2. And looking at the graph, and I'll do this in a different color marker. Each y value is half of the previous y value. Of course, half of 0 is 0. So the graph of 1/2 sine of x takes on this shape here. In general, the graph of the function of y equals sine bx or y equals cosine bx, where b is greater than 0, will have a period different from 2 pi when b does not equal to 1. So now we're going to look a little bit at the periods of these functions. We tend to put these functions in the form of a sine bx or cosine bx. Now, we talked about it being cyclical. Well, where the cycle ends, and the cycle in this case is this loop right here, because after you hit 2 pi, this graph repeats. That is considered to be the period of the function. And to get the period, it's typically 0 to 2 pi, but if b does not equal to 1, then we get that 2 pi over b is the period. So if we have y equals 3 times the sine of 2x, what we're looking at is we have a range from -3 to 3, and the period is 2 pi over 2, which is pi. So what we do here in graphing, and I need to get my black marker out, so give me a second. We go up to +3, go down to -3. So we come up, and we have to repeat the cycle here. So down -3. So we go up, down, up, down, and we were able to complete that cycle in pi units. So that also works from cosine as well. So that is the first part. If you look at 4.6 or page 4.6, it says find the period. The period is always 2 pi over b. Divide the interval into 4 equal parts. Evaluate the function for each of the 5 x values resulting from step 2. We have 1, 2, 3, 4, 5. Those are the 5 values that we're concerned about: the maximum, the minimum, and then where we are at the midpoint. And that's what it says next: maximum, minimum, and x-intercepts. They call it x-intercepts. I said midpoint, doesn't matter. Plot the points found in step 3, and then just make the same curve go along. So that's kind of what we did there. Not a big deal. So negative if you have y equals negative 3 sine of, and this time I'm going to get, well, let's make it negative sine of, I don't know, let's do 1/2 x. Now the range will be from -1 to 1. The period is 2 pi divided by 1/2, which is 4 pi. So now we're looking at having the period from 4 to 4 pi. So we come out here, here's 4 pi. 3 pi would be, well, I should actually, that would be 4 pi technically. That would be 3 pi. So I'll erase this here. And I'll also erase the 1/2 sine graph. And we're here, which means, and I'll graph this one in red, we stretch this out. So this becomes my value at 1. Then I go all the way to 2 pi. Now that's half the cycle, which it should be half the cycle because we've doubled the period. Then we come down to a minimum at 3 pi and then come back up to 4 pi. So we were able to complete a cycle of sine, and this again is y equals to negative, oh, I did something wrong, I apologize. I did positive sine, and this should be negative sine. So the negative sine, if you think about it, all of these y values, this is positive sine x, or sine 1/2 x, so we'll do negative 1/2 sine x. So we just reflect this graph about the x-axis. And we're there for a complete cycle. So, now, let's take a graph, and let's say we're given a graph and we want to interpret from the graph what the equation is. Now this is not one that's in the sheet. You can do it on your own. Now, I've only graphed one cycle. It's a positive sine graph because it starts off going up first. So we know it's going to be y equals, and we've got a positive sine value here. Now, think about what the range is. The range is from -2 to +2. So from that, we can say that it is 2 sine of x. Now, the period in this case does not have 4 in it. Does not have pi in it. It has 4. So we do know that the period is equal to 2 pi over b. And we're needing this b value here. So b is going to equal to 2 pi over the period. Now, in this case, the period is 4. So b is equal to 2 pi over 4, which is the same thing as pi over 2. So my formula here is y equals 2 sine of pi over 2x. So that's a good start. You can finish out the rest of The worksheet, it goes through page 4-9. After you hit page 4-9, it'll be 4.2, and that's what we'll look at doing in class. That would be Wednesday. So that's it for today, and hope you do well. And also, this is 4.1, so you can find the homework on 4.1 as well.